I want to continue my discussion of integral transforms, and in particular I will now be looking at the Laplace transform. So this is a very common transform, in particular to solve ordinary differential equations where the initial conditions are specified. Okay, because as you'll see, the Laplace transform is able to convert a differential equation to an algebraic equation. Okay, so essentially you have a differential equation, you take the Laplace transform, you then solve your algebraic equation to get your solution in the transform space, and then you transform it back to get the solution in the original space. Okay, so before starting, let me just recall that what we did before. We did the Fourier transform. In the Fourier transform, you can define, and this definition is not unique, it depends on what convention one is following, but you can define the transform as essentially this thing, okay, where you have some function f of x. This is how you can define the Fourier transform, and then you have some definition for the inverse Fourier transform as well. Okay, so given f of x, you can go to capital F of k. Given capital F of k, you can go back to f of x. Okay, and you saw essentially that how we can put this to use. Okay, and there are many other applications which we just don't have time to touch, but the hope is that once you know this basic mathematical detail, basic mathematical details, you'll be comfortable when you later on encounter Fourier transforms or Laplace transforms in your other courses. Okay, so the key point here is that if the Fourier transform may not exist, okay, because essentially this thing over here is an oscillatory function, okay, and so essentially this does not die off for large values of x. Either when x goes to infinity, this thing does not die off. When x goes to minus infinity, this thing does not die off. So unless and until f of x is dying off, this integral is not going to converge. So then your Fourier transform does not exist. Okay. In such a case, it may be the scenario that the Laplace transform exists. Okay, the Laplace transform is closely related to the Fourier transform in the sense that essentially this factor over here, okay, you instead of this ik, you just consider usually some real parameter, so that your function dies off. You have the original function, there's some decaying function multiplying that original function such that the integral converges. Okay, furthermore, you usually are not interested in your, for instance, your function. Your function is not defined from minus infinity to plus infinity. You usually have physically some initial time that you talk about. So initially, for example, if you have a harmonic oscillator, you kick the harmonic oscillator. The time at which you kick the harmonic oscillator you denote that as time t is equal to 0, and you are then interested in the future behavior of these harmonic oscillators. So actually, you are just interested in essentially the what happens from time 0 all the way to, for example, to time infinity. You don't really care about what happens before time 0. Okay, keeping this in mind as well, we could define the Laplace transform as, so I denote the action of taking the Laplace transform by this L. Okay, I denote it by L because once again the Laplace transform is a linear operation. So L acts on the function f, small f. Okay, so typically, conventionally, when you're talking about Laplace transform, you usually talk about the function f as being a function of t rather than being a function of x. Okay, so t is your independent variable. Okay, so when you take the Laplace transform of this function small f, you get by definition, so this you can take as a definition of Laplace transform, 0 to infinity for reasons that I just discussed, dt, okay, e raised to power minus pt, and then you have f of t. So this will give you a function of p. Okay, so in other words, you're going from the so-called t space, roughly speaking. You can say in these terms, you go from t space to p space. Okay, so your function which depends on t, after the Laplace transform, you get the new function which depends on p. Okay, right. Fine, so that's the definition of Laplace transform, just to get familiar with, and it's quite similar to the Fourier transform in the sense that given the function you can find out the Fourier transform, and then you can also find out the inverse in principle. Okay, it turns out that finding out the inverse of a Laplace transform is not that straightforward. You need to do a contour integral. Okay, but you can take a shortcut. You can kind of guess what function would you have such that when you take the Laplace transform, you get the function that you're staring at. Okay, so then you can figure out what's the inverse Laplace transform, as you'll see. Okay, but first of all, let's take some examples of what is a Laplace transform of some different commonly encountered functions. Okay, the first case that I do is for the simplest case, that my f of t is simply the constant 1. Okay, so the Laplace transform of f then is simply capital F of p will then simply be 0 to infinity dt e raised to power minus pt, because f of t is simply equal to 1. And then this integral, of course, all of you know how to do this, so you get minus e raised to power minus pt is going to be joint derivative divided by p. Okay, because when you differentiate e raised to power minus pt with respect to t, you're going to get minus p e raised to power minus pt. Okay, and then you plug over here 0 to infinity. When you throw in infinity for t, you're going to get 0. When you go throw in 0, you're going to get 1. So this thing is just going to give you 1 over p. Okay, what if f of t is some other constant? Well, never mind. We know that the Laplace transform is a linear operation. Why do we know that? Because if you have c1 f1 plus c2 f2, where f1 and f2 are arbitrary functions, then you have by definition pt c1 f1 t plus c2 f2 t. Okay, and then you can write this as dt e raised to power minus pt c1 f1 t, okay, plus c2 e raised to power minus pt f2 t. And then you can chop up this integral into two integrals, bring out the constant c1 and c2. So you have c1 0 to infinity dt e raised to power minus pt f1 t plus c2 e raised to power minus pt f2 t. And this, of course, is c1 times the Laplace transform of f1 plus c2 times the Laplace transform of f2. That's what I meant when I said the Laplace transform is linear. Okay, so in other words, having found the Laplace transform of f of t is equal to 1, what's the Laplace transform of f of t is equal to 5? That's just 5 times this thing, 5 over p. Okay, right? Okay, so the next non-trivial case that we have is what happens if we have the Laplace transform of f of t is equal to t. Okay, then capital F of p, in this case the Laplace transform is going to be dt e raised to power minus pt times t. Okay, now you can do an integration with parts, but as we have seen before, there's a smarter way to do this, which is just to differentiate under the integral sign. To see that, recall that we just derived that this thing is 1 over p. If I differentiate both sides of this equation with respect to p, what do I get? I get of course this thing. This derivative over here, you can bring it inside the integral. Okay, so then it becomes a partial derivative with respect to p of this thing, of the integrand. Okay, so this implies that you have p e raised to minus pt dt is equal to, and then I can take the derivative on the right hand side. This thing is minus 1 over p square, of course. When you take the derivative over here with respect to p, of course, minus t comes down. Okay, and you can push the minus sign outside the integral, so the left hand side becomes t e raised to power minus pt dt is going to be equal to minus 1 over p square. Or in other words, this thing is simply equal to 1 over p square. In other words, the Laplace transform of t, let me just write it like this, f of p is equal to 1 over p square when f of t is equal to t. Okay. Right. I can carry this procedure further. So what if I have 0 to infinity t square? So I'm looking at the Laplace transform now of t square. Right. What is this equal to? Well, I start from the previous one, which I know. I have this thing. This is equal to 1 over p square, as we have just seen. Differentiate again with respect to p. So quickly doing this, the derivative on the left hand side goes inside. When you differentiate with respect to p, you throw in another factor of minus t. So you have this thing, and this thing is going to on the right hand side is going to give you minus 2 over p cube. Okay, so this immediately implies cancelling out the minus signs. This immediately implies that t square e raised to power minus pt dt is going to give you 2 over p cube. So the Laplace transform of t square is 2 over p cube. Okay, of course here I am assuming that p is bigger than 0, otherwise the integral is not going to convert. Okay, right. Going on, if you have the Laplace transform of t cube, right, if this is what you need to find, then you know what to do. You take the previous one, differentiate it with respect to t, so you get essentially t square, and then you have minus t e raised to power minus pt dt. Okay, I'm differentiating this one. This is going to be equal to 2, and then you have minus 3 over p raised to power 4. Okay, and the minus sign cancels, and you have that this thing is equal to, and that this implies that 0 to infinity t cube e raised to power minus pt dt is equal to 6 over p raised to power 4. Right. Okay, so the pattern should be very clear. The Laplace transform of t raised to power n is simply given by n factorial divided by p raised to power n plus 1. Okay, that's the Laplace transform of for any power of t. In general, of course, if n is not an integer, then you need to use the gamma function. Okay, so that's what you have. Oops. So we have p raised to power n plus 1 over here. Okay, so this gives you a nice simple way of essentially of getting the Laplace transforms of any power of t. Okay, you just differentiate under the integral sign. Similarly, if you have over here as further example, you have of course f of t. So you have e raised to power minus at. Okay, then what's the Laplace transform? So the Laplace transform in this case, again going back, whenever I do this derivation, you always go back. I'm always assuming that the integral converges, so go back and look at the conditions when the integrals do converge. Okay, so like I said, if you're looking at the Laplace transform, for example, for 1, okay, this one, okay, which we found that this is equal to 1 over p. This is only valid when p is bigger than 0. Okay, because otherwise this integral is not going to converge. Okay, if p is less than 0, then of course it's going to blow up. Okay, at infinity. Okay, so given this function, again you just use the definition e raised to power minus at, and this is of course 0 to infinity e raised to power minus a plus b times t, and you know what this is going to be. Previously we integrated e raised to power minus pt, now I'm integrating e raised to power minus a plus pt. This thing is just going to give you 1 over p plus a. okay, because when I had only e raised to power minus pt, when I only had this thing, I was getting 1 over p. When I have e raised to power minus at along with as well, I can combine the two exponentials, you get e raised to power minus a plus p, and so the Laplace transform is going to give me 1 over p plus a. Okay, right. So you have this thing, and what else? Similarly, you can easily see that if you have the function is of the form t raised to power n e raised to power minus at, you have to find the Laplace transform of this thing. You can get 0 to infinity dt e raised to power minus pt t raised to power n e raised to power minus at. This exponential can combine with this exponential, and you know how to do this integral already. You are getting this result when a is equal to 0. When a is not equal to 0, of course this exponential combines with this exponential, and you can easily guess, and you can check rigorously if you want, that you are going to get p plus a raised to power n plus 1. Okay, so that's what we have for the Laplace transform of this function. If you want to find out the Laplace transform of some trigonometric function, so suppose f of t is equal to sine of at, how do you find out the Laplace transform of this thing? The easiest way is to first of all consider instead f of t is equal to e raised to power iat. Okay, and then I can take the imaginary part to give me the Laplace transform of the original function that I want. So the Laplace with this f of t, I know that the Laplace transform is now going to be 0 to infinity dt e raised to power minus pt and e raised to power iat. Okay, this is a very easy integral to do because you can combine the two exponentials. Okay, and so I'm going to get 1 over ia minus p, right? And then I have over here e raised to power ia minus pt from 0 to infinity. When t is infinity, assuming that p is bigger than 0, this thing is going to give me 0. This whole exponential is going to give me 0. And when t is 0, this whole thing is going to give me 1. So I'll end up with 1 over ia minus p minus 1, which is going to give me 1 over p minus ia. Okay, fine. I can then write this as p plus ia, p minus ia, p plus ia, because I have to take the real and imaginary part later on. So this will give me p plus ia over p square and plus a square. So if I want the imaginary, if I take now the imaginary part of this thing, I'm going to give 0 to infinity dt e raised to power minus pt sine of at, which is precisely the Laplace transform of this thing, and that in turn is going to be the imaginary part of this thing, which is simply a over p square plus a square. So in other words, given f of t is equal to sine at, the Laplace transform is a over p square plus a square. We have also found the Laplace transform if you start it off from a cosine. So if f of t is equal to cosine at, then we have figured out that the Laplace transform is given by p over p square plus a square. Okay. Now, before moving on, in principle, you can find out the inverse Laplace transform by doing a contour integral, like I just said before. For details, you can look at ODEs chapter 14. It's essentially usually called by the name of Bromwich integral, the integral that you need to do. But in practice, you don't usually do that. What you do is essentially you look up a table of Laplace transforms. So given there are whole tables that are available. So given most type of function that you encounter, you have correspondingly listed along with that function the Laplace transform of those functions. You can find such a table in ODEs as well. Okay, I believe it's the chapter on ordering differential equations where you will find it. Okay. And well, so if you have such a table, you can very easily find out the inverse Laplace transform. You just read the corresponding entry in the table. And we can already kind of do that. So if, for instance, if we have f of p is equal to 5 over p and ask you what is small f of t, well, you say, okay, if f of t is 1, then correspondingly f of p is 1 over p. Okay, and I can go backwards. So if I know then that the Laplace transform is 1 over p, and somebody asks me what's the original function, I'll just say, okay, the original function is just the constant function 1. If somebody says that the Laplace transform is 5 over p, then you'll just say that the original function is 5. Okay, so that's how you can kind of guess what the original function is given the Laplace transform. Okay, if you're not able to guess, just look up the table. Okay, if you're not even able to do that, then you just you just have to do that contour integral. Okay, but usually in practice you don't need that. Okay, so similarly, just to drive home the point, if somebody says that okay, f of p is equal to n factorial over p raised to power n plus 1, what is f of t? Well, you look around for what's the function that gives you this Laplace transform. Have we already done that? I think we have, because essentially here it is. What function were you dealing with? You're dealing with t raised to power n. So the Laplace transform of this thing is simply t raised to power n. Okay, right? If somebody says that the function that the Laplace transform is simply 1 over p raised to power n plus 1, never mind, this is just a constant, and then you can accordingly adjust f of t. Okay, now by far the biggest use of Laplace transforms is to solve ordering differential equations with some non-homogeneous term. Okay, the beauty is that you can very easily deal with any kind of non-homogeneity term can be of any kind. Okay, so the right hand side of the ordinary differential equation can be any function whose Laplace transform you can easily find. Okay, so for example, let me do an example. You have this equation. Okay, 4y prime plus 4y is equal to t square e raised by 2t. Let's do this using Laplace transform. The idea is very similar to how we dealt with differential equations when we're doing Fourier transform. You just take the transform everywhere. Okay. Before I do that, let me give you two key results. Okay. You have the Laplace transform of this function y of t is, I denote that as capital Y. So this is actually a function of p. Okay. What's the Laplace transform of the derivative of y? Well, you go to the definition. So you have e raised to power minus pt, and then you have this y definition. Then you do an integration parts. You throw this derivative onto this exponential. You pick up a minus sign. So you have d by dt of only of e raised to power minus pt, and then you have y. Okay, and then you also have the boundary term, which is e raised to power minus pt, y, and then 0 to infinity. Okay, and these of course the 0 to infinity refers to values of t. Okay, now this first term over here, when you take the derivative, minus p comes down, the minus cancels the minus sign outside, so you're left with 0 to infinity dt p. Okay, p is there, and you have e raised to power minus pt times y. Y of course is a function of time, so let's just make delta explicit. And you have plus, so you have when t is infinity, you are going to get 0. When t is 0, you're just going to get 1. Okay, but along with the minus sign when you take the limits, and you're going to get y at time 0. Okay, so you're going to get that. Okay, right, now in the first integral this p goes outside. What is left is essentially the Laplace transform of y, which I denote as capital Y as before. Okay, and so you get that this thing is y0. Usually we denote for simplicity this thing is simply y0. So y0 is the value of the function y at time at t equals to 0. Okay, so this is p capital Y minus y0. Okay, what's the Laplace transform of the double derivative of y? Okay, so the Laplace transform of the double derivative of y is easy to find, okay, because the Laplace transform is linear. So the Laplace transform is easy to deal with. What you have then over here is that you can just use your previous result to guess that this thing will be P times capital Y prime minus Y naught prime. Okay, so essentially where Y naught prime is essentially the value of the derivative dy upon dt at the initial time. Okay, you just use this because you can kind of guess that exactly the same derivation holds true, except that you have the double derivative over here, so you transfer one derivative to that side, okay, and then you're left with dy by dt. So instead of y of t over here, you have dy by dt. Instead of y naught over here, you have dy by dt at time t is equal to 0. So that's why you end up with capital Y prime over here and Y naught prime over here. Okay, that's what I have over here. You can just do it more rigorously if you want. Okay, but we know capital Y prime, that is equal to this whole thing. Okay, so this thing is Py minus Y naught minus Y naught prime. So this thing is P square capital Y minus P Y naught minus Y naught prime. Okay, so that's the Laplace transform of the double derivative. Okay, and now I can finally go back to the differential equation that I want to solve. Okay, so the differential equation I want to solve, I take the Laplace transform both sides. I get essentially y double prime plus 4y prime plus 4y is equal to the Laplace transform of t square e raised to power minus 2t. Okay, because the Laplace transform is linear, the left hand side becomes the Laplace transform of y double prime plus 4 times the Laplace transform of y prime plus 4 times the Laplace transform of y. Now to actually find out the Laplace transform of y prime and the Laplace transform of y double prime, I need to know the initial conditions. Okay, so usually when you are asked to solve a differential equation, you also specified what are the initial conditions. Okay, so in case because in the case where you're not looking for the general solution. Okay, so here let's take the initial conditions to be that the value of the function at time t is equal to 0 is 0, and so is the value of the derivative. Okay, in this case the Laplace transform of the double derivative, this thing is very simple because this term becomes equal to 0 and this term is also equal to 0. Okay, so we then get that you get p square y plus 4 times, and the Laplace transform of y prime is also very simple because this thing is 0. Okay, so you're only left with this thing plus 4py plus 4y is equal to the Laplace transform of t square e raised to power minus 2t. And so the left hand side has just become an algebraic equation. I can factor this out. So you have 4p plus 4 is equal to the Laplace transform of t square e raised to power minus 2t. And so capital Y of p, okay, is given by the Laplace transform of t square e raised to power minus 2t divided by p square plus 4p plus 4. But p square plus 4p plus 4 is simply equal to p plus 2 whole square. So I have over here this thing. Okay, now to proceed I just need to figure from capital Yp y of t. Okay, so I just need to take the inverse Laplace transform. Okay, proceed in two different ways. Let me first simplify this numerator over here. Let me first find out the Laplace transform of t square e raised to power minus 2t. Okay, what's the Laplace transform of that? Well, we remember we had the Laplace transform of t raised to power n e raised to power minus at, okay, is going to be equal to n factorial divided by p plus a raised to power n plus 1. Okay, so this numerator over here is exactly of this form. So I get that capital Yp, I can write that as essentially over here n is equal to 2, so I get 2 divided by, and a of course is 2 as well. Okay, so you get over here p plus 2 raised to power 3. Okay, that's the Laplace transform of the numerator over here. Okay, and then of course you have the denominator, so you have to put that in as well. So you get this thing, and so the whole thing is p plus 2 raised to power 5. Okay, so that's the Laplace transform. Now from this I need to figure out the y of t. So essentially I need to hunt around that what is y of t such that when I take the Laplace transform I get capital Y of p. Okay, well this looks very familiar, very similar to this thing, right? So in the sense that when I take the Laplace transform of sum of t raised to power n e raised to power minus at, I get something that looks very similar to this thing. Okay, so my first guess would be, okay, that the function, that let's try to guess a function such that when you take its Laplace transform you end up with this thing. Okay, so first of all I have this factor 2, so let's just write 2 outside. Okay, and then I would guess that I would need t raised to power 4, okay, e raised to power minus 2t. That would be my initial guess, okay, which probably needs to be adjusted a little bit here and there. Let's see. So the Laplace transform of this thing will be 2, and then applying this thing that we have over here, the Laplace transform of t raised to power 4 e raised to power minus 2t will be 4 factorial divided by p plus 2 raised to power 5. Okay, so it's almost what we wanted over here, except that you have this extra 4 factorial, but never mind, you just divide both sides by 4 factorial, so you can get rid of this extra 4 factorial. So in other words, y of t is simply this. That's your y of t. Okay, right? Alternatively, I can use the convolution theorem. Okay, so remember that for Fourier transforms we found that the product of two Fourier transforms okay, is equal to the Fourier transform of the convolution of the two original functions. Okay, for Laplace transform you have a very similar statement. Okay, the proof is very similar as well. Okay, so if you are interested you can look up the proof in for example Boas. Okay, but you should be able to do the proof yourself. Essentially it says that given the product of two Fourier transforms, this is equal to the of two Laplace transforms, sorry, over here, this is equal to the Laplace transform of the convolution of small f and small g. Capital F is the Laplace transform of small f, and capital G is the Laplace transform of small g. That's what the convolution theorem says. Okay, so in other words, we can write down y of p is equal to Laplace transform of t square e raised to power minus 2t. Okay, if I'm not mistaken, yes, and you have over here divided by p plus 2 whole square. So identify over here your f. Your f is going to be simply the Laplace transform of so I identify over here capital F of p is given by 1 over p plus 2 whole square. So in other words, then f of t that goes over here is the inverse Laplace transform of capital F. Okay, and this thing, by looking at our good old expression this, we can guess that this thing will be t e raised to power minus 2t, and you can check that when you take the Laplace transform of this thing you will get that thing. Okay, okay, so the other thing is that what is gp is of course the Laplace transform of t square e raised to power minus 2t. This immediately implies that g of t is simply t square e raised to power minus 2t. Okay, now applying the convolution theorem is usually easier because the original problem calls for the taking the Laplace inverse transform of the product of two functions. That might give you a complicated function whose inverse Laplace transform you have to find. Okay, but it should be easier to calculate the inverse Laplace transform of one of those individually. Okay, one of those Laplace transform is of course trivial to do over here, as you saw over here. okay, in this example. The other Laplace inverse Laplace transform might be more complicated as in the inverse, but it's still easier than, in general, easier than the product of capital F and capital G, because that's what the convolution theorem is useful when you're looking to find out the inverse Laplace transform. So anyway, so then we know from this convolution theorem that the inverse Laplace transform of capital Fp, capital Gp is just given by the convolution of small f with small g, and this by definition is simply equal to 0 to t d tau f of t minus tau g tau. Okay, so let's just plug now what we have. So you have 0 to t d tau ft minus tau is simply t minus tau e raised to power minus 2 t minus tau. Okay, g of tau is tau square e raised to power minus 2 tau. Okay, right, fine. And then you are going to have essentially 0 to t tau. You are going to get over here t minus tau, and then you in the power over here you're going to get e raised to power minus 2t, and then e raised to power plus 2 tau, but that e raised to power plus 2 tau is going to be cancelled by this, so you're left with this thing. Okay, right, and then I can split this thing up into two parts. Okay, so I have over here essentially before I split it up into two parts, this thing only depends on t. T is there, the upper limit, okay, and the integral is over tau. So I can pull this e raised to power minus 2t outside the integral. Okay, so then I'm left with 0 to t d tau t minus tau t square tau square. So this is a very simple integral to do. You are going to get 0 to t d tau, and then you'll get tau square, and then I can pull the t outside this integral, minus 0 to t d tau, and then you have tau cube. Okay, so when you do this integral, you're going to get t, and then you're going to get tau cube over 3, and then when you put in the limits, you're going to get t cube over 3. Combine that with the t outside, you're going to get this thing. When you do this integral, you're going to get t raised to power 4 over 4. Okay, so the whole thing then is y of t is just going to be given by e raised to power minus 2t, and then you have t raised to power 4, and then you have 1 by 3 minus 1 by 4, and this thing is 4 by 12 minus 3 by 12, which is 1 by 12. So this is 1 by 12 e raised to power minus 2t t raised to power, exactly the same as before, because essentially when you have this thing, 4 factorial is 24, so 2 divided by 24 is 1 by 12. Okay, right. Okay, so with this in hand, I can look at differential equations with fancy kinds of with the fancy kind of right hand side, right? So essentially, for example, you can have something like the harmonic oscillator equation. So for example, I can have I can have d2y by dtt plus omega square y is equal to some driving term. Okay, so this is a driven harmonic oscillator with some time dependence f of t. Okay, so to begin, I also specify the initial conditions. For simplicity, I take these as the initial conditions. So the harmonic oscillator is initially at rest, and I set up my coordinate system such that its initial position is also 0. Okay, now I take as this thing, I take that as delta t minus t naught. Okay, as a Dirac delta function. Now you might say that is unphysical, but you can model your driving term by a Dirac delta function very well in many scenarios. Okay, so for example, consider you have a ball and you kick it. Okay, so of course your foot is in contact with the ball for a very short time, and the force acting that you exert on the ball is quite large during that that short time. Okay, so we model the force that you exert on the ball as, you can model it as something like this, where t naught is the time at which you kick the ball. Okay, yes, this thing blows up at t naught, yeah, but the effect of this force is still very well defined, because remember, by Newton's second law, you have, this is the change in momentum of the ball rate. So the force acting on the ball is the rate of change in momentum of the ball. So the change of the momentum of the ball is given by the integral of the force. So suppose you kick the ball at 3 seconds on this horizontal surface, and I ask what's the total change in momentum of the ball from t is equal to 0 to t is equal to 3 seconds. Okay, so assuming that this surface is frictionless, once you have kicked the ball, there is no other force acting on the ball, and so we have these as the limits. Okay, and you have kicked the ball at 2 seconds, so you just plug this thing in. So you have f naught delta t minus 2 dt. F naught is a constant that goes outside, and the integral of the delta function gives you 1, so you just left with f naught. Okay, right, so the change in momentum is simply equal to this constant f naught. Okay, now be careful over here. You might say that there is some problem with the dimensions over here, that of course this has dimensions of momentum, this has dimensions of force, but actually this does not have dimensions of force, because the Dirac delta function has dimensions of inverse time over here. So you can see that from this relation, this has to be equal to 1. This has dimension, dt of course has dimensions of time, so, and this is dimensionless, so this thing needs to have dimensions of inverse time. Okay, so in other words, when I wrote down this thing has dimensions of inverse time, this thing has dimensions of force, so this thing needs to have dimensions of force multiplied by time. Okay, so this is actually has dimensions of force multiplied by time. Okay, and force multiplied by time, as you can see from ft dt is equal to dp, force multiplied by time has exactly the same dimensions as that of momentum. Okay, so we are fine. Okay, but you have to be careful about, a little bit careful about dimensions when you have Dirac delta functions. Okay, now I look at my linear differential equation. For completeness, I'm doing it with the harmonic oscillator. Okay, so this is equal to delta t minus t naught. So there's a driving term which is a Dirac delta function. To handle this, I just do Laplace transform on both sides. So you can see immediately that in the transform space, okay, the Dirac delta function, you can tame it. Okay, the Dirac delta function in the original, the time space, the original t space is not such a nice function, because it's 0 everywhere. It just blows up at t naught. Okay, but in the transform space, it is becomes a perfectly nice function, as you'll see now. When I take the Laplace transform, because of the initial conditions that I have over here, this first term just becomes p square times y. This thing becomes omega square capital Y, and this is the Laplace transform of delta t minus t naught. To find out this Laplace transform, I can go do the definition, use the definition of the Laplace transform. So I have e raised to 1 minus pt delta t minus t naught, and then the action of the delta function means that you just, wherever you see t in the integral gets killed off, and wherever you see t, you replace that with t naught. So this is simply e raised to minus pt naught. So you have then p square y plus omega square y is equal to e raised to minus pt. So you see, this is a nice function to deal with. It's a nice function, nothing weird about this. And so you can see that the Dirac delta function originally, which is a weird function, in the new transform space, in the p space, so to speak, it becomes a perfectly nice manageable function. So anyway, proceeding, capital Y becomes e raised to power minus p t naught over p square plus omega square. Okay, and you can check that the inverse Laplace transform is simply sine of omega t minus t naught divided by omega. Okay, you can immediately see the sign, because remember we did this, the Laplace transform of a sine way back, way back. There you go. Okay, so we did the Laplace transform of the sine. Okay, so that is just some constant divided by p square plus a square, and so because of the p square plus a square in the denominator, we expect that that because you have p square plus omega square over here, that's why you're getting the sine over here. Okay, and this omega in the denominator is just to cancel the omega in the numerator once you take the inverse Laplace transform of 1 over p square plus omega square. Okay, right, and this thing in the numerator just tags on an extra thing in the argument. You can check this, okay, or you can use the convolution theorem. Okay, so that's also fine to calculate the inverse Laplace transform. Okay, anyway, so this is your solution to your differential equation, this differential equation, right? Now a solution to your linear differential equation with the so-called driving term or the source term on the right hand side being equal to a Dirac delta function is called the Green function. Okay, so Green function means that you have a linear differential equation, so you have L acting on y. Okay, right, so you have some linear operator, not the Laplace transform. So this, just so that I prevent confusion, let me use some of the simple L x and y. So this is your linear differential operator. Okay, it acts on y to give you delta something like this. Okay, then in that case y is called the Green function. Okay, right, what this means is that you're solving the differential equation for the case where the driving term is non-zero, is almost always non-zero except for the case when t is equal to some particular time. Okay, so just for future convenience, let me just do a change of symbols over here. So usually this is written as delta t t minus t prime, which you can also write as, because the Dirac delta function is even, you can also write it like this. Okay, so I just replace t naught over by t prime. Okay, you do that because essentially you very soon we're going to do an integral over this argument, and it's a bit weird to do the integral over t naught, because usually t naught denotes as a it brings to mind some initial time. Okay, rather than your integration variable. Okay, so anyway, but if you want, you can just integrate over t naught, as you will see. Anyway, so so the Green function, so if you have this solution, this equation, then this solution, this y, which obeys this equation, I'll remember is a linear differential operator. Y which obeys this equation is called the Green function. It's a function of t and t prime, of course. Okay, right, and just to make it more concrete, here we have already found out the Green function for your harmonic oscillator problem. Okay, so you have this problem, you just replace by t naught by t prime, and that is your Green function. So for the harmonic oscillator, g t prime is simply equal to sine omega t minus t prime divided by omega. Okay, now why are we so interested in finding out this Green function? Okay, it's essentially because, remember that when we were solving linear differential equations before, I told you that if you have different driving terms on the right hand side, you have the sum of those, you can find out the solution by treating each of those terms individually. Okay, and it turns out that any function on the right hand side, so in actual fact you might not have a Dirac delta function on the right hand side of the differential equation that you want to solve. So suppose you have this thing, okay, right, with some arbitrary f of t. Now f of t I can always write as this. So you have 0 to infinity f t prime delta t prime minus t dt prime, right? By using the definition of your Dirac delta function. Okay. And so I'm assuming over here, of course, that the force is 0 anyway for times less than 0. Okay. So this driving term or the source term is written as a sum over Dirac delta functions. Okay. And then my guess would be that the solution to this differential equation I can also write down as a sum over the over the solutions to each of these terms within the sum over here. Okay, so the solution to each of these terms is something that looks like the green function. Okay, because the green function explicitly is a solution when you have just one Dirac delta, and the full solution will be a sum of all you sum up over all these solutions. Okay, so my guess would be that you have something like this. Okay, so you have g t t prime and then f t prime d t prime. Okay, that is what my guess would be, that this is the solution. We can very easily check that this is indeed the solution. You just apply on both sides the linear differential operator. So on the left hand side you have Ly, and then you on the right hand side you have g t t prime f t prime. And remember that L, then you can take inside, and remember that L contains derivative with respect to t, not with respect to t prime. Okay, and so this you can write as 0 to infinity dt prime L g t t prime. Okay, because that's the only term that contains t, and by definition of the Green's function, the way that we have defined it, this thing is simply delta t prime minus t. Okay, that's what I meant when I previously said that you'll be seeing integrals with respect to this second argument in the Green's function. That's why I changed this t naught to t prime. Okay, so that it looks more like a usual integration variable. Okay, and this thing, of course, by using the definition of your Dirac delta function, this thing is f of t. Okay, right? So that's essentially what we have. So this y that you've written down like this is indeed a solution to the differential equation that you wanted to solve. In other words, if you have solved for the Green's function, then you can immediately find out y for any kind of driving term. Okay, all you need to do is then just to find out this integral. Okay, so that's why Green's function is so useful, so that you don't keep on solving the same problem again and again and again. Rather, you find out the Green's function, and then no matter what kind of driving term you throw at your problem, you can very quickly find out what the behavior of your system is by finding small y. Okay, but remember, the Green's function does depend on the so-called boundary conditions, because remember when we found this thing over here, we were already using the fact that y naught and y naught prime are 0. Okay, when we found this. Okay, I explicitly wrote it, but okay, that's what I was assuming to begin with. Okay, so that's what I wrote. Okay, so the Green's function, remember, so if you change your boundary conditions, you better once again find out the Green function. Okay, it's called Green function as well, like Green's function. Okay, so that's what you have. Okay, so that was a very brief introduction to Green function. The idea again is that when you have a driving term, you find out the Green function, you have essentially solved the problem for all kinds of driving term. One final point I have to warn you about is that usually the Green function is a piecewise function. So this thing you have to define it for different values of t, okay, as compared to t prime. So here I just very quickly wrote down that for the simple harmonic oscillator problem, that's my Green function. But of course I obtained this from the Laplace transform. But I have to be careful when I write this down. Okay, it actually turns out that this thing is true if your t is bigger than t prime is bigger than 0 and less than t, okay, and the green function is 0 if your t prime is bigger than t, okay. So, and once you take the inverse Laplace transform, you immediately see why that is the case, okay. Okay, so you have to be a bit careful when you apply this thing, okay, because when you are going to do this integral, you need to have this green function defined for different values of t prime, okay. So this integral, rather than going from 0 to infinity, is only going to be in this case from 0 to t, because only from 0 to t is this thing non-zero. If t prime is bigger than t, then this thing becomes 0, okay, right? Fine. And so that's essentially all that I'm going to say about Green's function, okay. So next we are going to move to partial differential equations, okay.